My name is Michael Okyen. I am a software engineer at Plexus. We are a design manufacturing company. We mostly do devices in regulated industries, so working for companies like Johnson & Johnson, GE Healthcare. I work on a lot of medical devices, so I'm an embedded guy. That's my perspective on things. It says Michael Okyen up here, but I want to acknowledge that Matt St. Clair is a colleague of mine, and he's been a huge collaborator. He just doesn't like to present as much as I do. So I'm here today. So this is the first time I'm giving a talk, but I'm really looking for collaboration. This is something that's a work in progress. So please, give me some questions. Maybe not quite as many as David's last night if you went to that talk, but let's have some fun today. So we all want to write good code, right? I mean, we know that when we write better code, we end up with a better software product. We get more fulfillment. We get more fun. It's just more fun to write good code. And we know that the future is better, whether that's our next feature, whether that's 6 months down the road, whether that's 5 years down the road when you come back. So why don't we always write great code? Well, the long and short is that it's not easy. If it was that easy, we probably would always write great code, right? So our goal is to write good design, but this is not a trivial task. There's a lot of artistry to it to some degree. You could say that software engineering isn't art, but that's a challenge. We don't want to wait for people to get to the point of having experience in order to know what something's good. So we're going to talk about that. This is something we've been developing a design philosophy for the last few years, a few of us within Plexus. And I want to share that with you today. And hopefully we can get some feedback. Maybe you'll learn something. Maybe I can learn. I'm hoping to learn something from you guys too. So if you're interested in what I have to say, I do have a website. Thanks to Brayden, who's here today, who inspired me at CppNow to come up with a website. If you go there right now, there's not a lot on it. I'm hoping after this talk, get some feedback from you guys. In the next 2 weeks, I'll start posting some of the blogs about this and maybe other things in the future. But my last name, Okyen, rhymes with token, so open source software. That's about as witty as I can get there. All right. So where are we going today? So first, we're going to talk about some of the challenges with software design. What makes it something that's non-trivial for us to do? And then we're going to talk about decision-making isolation. This is the design philosophy that we've come up with. As part of that, we're going to talk about invariance and get into kind of a revised definition of that, or maybe a more detailed definition. And then we're going to talk about unit testing. So how we do unit testing within this idea of decision-making isolation. So my software journey started a little bit atypically. I actually went to school for my undergrad and grad school in mechanical engineering. Truth be told, I hated my first software class. Didn't get it. Objects, what is this thing? No interest. But then I got into control algorithms, and if you like control algorithms, what is one of the coolest things you can control? Well, robots, of course. And then turns out that in order to control a robot, you write software. So coming out of grad school, I got a couple jobs where I had different titles, controls engineer and systems engineer. So these are some of the different robots that I got to work on. And then eventually came to Plexus in 2016 and decided I would have my Pinocchio moment and be a real software engineer and really fully commit to that. So I can look back in the last dozen or so years where I've been writing code, all the way from writing LabVIEW and MATLAB to my days of writing C/C++. That irk anybody in the room? No, it's a hot topic, right? But you can certainly write C++, kind of more like C when you really don't understand either language very well. And that's what I did for a while, all the way through my everything is OO phase. And I can look back at that path and come up with 4 to 6 times throughout that time where I thought I knew what good software looked like. And then I think that got me in something that looks a little bit like this. I'd start out, I think, okay, been doing this a little bit, got my things cleaned up a little. I think I know what good software looks like. And then I'd write a little more code and learn a little bit more. and then question everything I know. and then learn a little bit more, write a little more code, and then feel like maybe I've got some better idea. This is frustrating, right? 4 to 6 times in 12 years. Now, I get it. I came from a non-classical software background, so I had a lot to learn. And hopefully these cycles are getting smaller and smaller, and maybe I'm also getting less confident that I know what quality software necessarily looks like, or less definitively clear that I have the answer. But this is a challenge. We don't want to keep doing this. Anyone had this experience where you've looked back at code you wrote 5 years ago, ugh, anybody? Yeah. Yeah, I could probably do that code I wrote very recently. But then I came to Plexus and I found it. I found the silver bullet. This was going to fix everything. Anyone want to take a guess as to what the silver bullet was? Unit testing. This is it. Boom, done. No longer do I need to build the code, deploy it on the robot, drive the robot tank out into a field, and go run it for 20 minutes to figure out, yeah, I think I fixed the bug. Cool, I'm gonna be able to test everything in my development environment and know that my code's good to go, right? That's how this works. Boom, test everything. That's, if you read some books and blogs, they'll say, boom, you should be able to run your unit tests. When those pass, ship it. I'm an embedded guy. I certainly have other things. My environment is not my development environment. So there's an added piece there. But I don't think that's the case in most of the time either, regardless of your environment. But this was the idea I had for a little while. This was actually an image I had on a presentation I gave at my work. Maybe I didn't completely believe that 100% was the right answer, but still, this is what I thought. But of course, we know that as you go and do that, anything you add has its own baggage. We know that as you start adding more unit tests, now you can have coupling. And certainly I can tell you the way I wrote unit tests, I definitely had coupling. I definitely had dependencies. I definitely had this fragility that I'd created by trying to test everything down to, yes, that function does return the same const every single time. So I had this conversation with a couple of my colleagues, Matt St. Clair being the foremost one, and we realized we needed to change our unit testing focus. This wasn't the right way to do this. And Matt really had this idea that we needed to test to get more value. We needed to test the things that were going to increase our confidence the most. So we came up with this revised focus. To be skilled at unit testing, we need to focus on getting better at choosing what code to test and designing code that is testable rather than getting better at writing more complex tests. If you've ever spent time really digging into Google Mock, there is some interesting stuff in there. You start getting into in sequence. Oh, I can choose this. Death test, sweet. There's a lot of complicated things in there. If you're having to go to those means, most of the time, that's probably more a design problem, right? So I got ready to submit this talk, and then I actually sent a message to Klaus Igelberger, who I had the pleasure to meet last fall and talk with him for a while. And he said, you know what, I think you're on the right path, but this is a design problem. This isn't a unit testing problem. If you do what you're talking about doing, then I think you're gonna come up with better design. So again, work in progress, right? This is something that I am executing when I write code right now. There's a couple other people that are. We haven't delivered this out on a whole project yet. I'm hoping to do that later this year. Hopefully you guys can help me get better at this and maybe answer some of the questions that I have. But this is a work in progress right now. So I don't even tell you that I could tell you that I have all the answers, right? So if we're going to talk about writing good code, I think that then we need to have a definition of what good code means. So this was one that Klaus Igelberger gave 2 years ago. The high quality software is easy to change, easy to extend, and easy to test. I think it's a great answer. I think it's a great definition, and far be it from me to question Klaus. But I want to say just for today, I'm not proposing that this is a better definition, but just for today, I want to say that I would add one more thing, which is readability. Because to me, someone who comes along and uses your code next, who may need to add another feature or do a similar feature, or they need to debug it, or just needs to use code that you've written, they need to be able to read it as well. So I think I'm going to propose that quality software is easy to read, modify, extend, and test.
Do you want to spend some time talking about it?
Nope.
Okay.
Nope.
Can I add one more item?
Sure.
It works. Right? It actually does the thing it's supposed to do.
I can't argue with that. I think for today, I can't update my slides again before we keep going. But yes, that would be the absolute litmus test. Does the code do it? You could certainly get into performance. Does your code perform acceptably well?
That's part of does it work?
And as Tony mentioned, not all of our code needs to be performant, right? There's places where it does and places where it doesn't. So
you could argue that the code working is an extension of the test part.
Yeah,
right?
The test actually passed.
That's how you know
Not
it works.
easily to test, but easy that the test actually passed.
Yes.
yeah.
Wouldn't you say that readability is implicit in the ability to modify and extend it?
Yes, I think that is implied, but I want to, for today, I want to separate that and consider it separately, just because I want to put a little more emphasis on that in the context of this presentation. Yeah. Absolutely. And I think that you could find lots of other definitions. We could do a whole talk just on what does quality code mean. But you guys okay if we agree that this is the one we'll go with for the next hour? All right. So when we talk about software design, this is not a new topic by any means, right? So what are some acronyms? I'm asking you guys. What are some acronyms that come to mind when you think of software design? Solid.
Big one.
That's a big one.
KISS.
KISS. Dry.
Is that KISS with a Y or an I?
I was gonna.
Are you going to tell us what these mean?
Yeah. Any others?
Probably.
All right. So this is my list that I came up with quickly. So solid, principles of design, don't repeat yourself, keep it simple, silly. Yagni, yankin' and eat it. I'm from North Carolina, that's how we say it, but you can say it differently if you want. Damp was a new one to me. There's some people online that say your production code should be dry, but your test code should be damp, where it should be more descriptive and repeating things makes your tests more explicit. So I thought that one was kind of cute. Then there's grasp and Cupid, which I don't know a lot about, but those are similar things to solid, kind of in that general design principles. So the solid principles, we're going to talk about those a bit more. So the solid principles really kind of came together around 2000. I think it was Robert Martin that kind of pulled these together, although the concepts have been written about for more than a decade, more than that. So when I look at these 5 principles, the LID, I feel like I have a pretty good handle on. I feel like I know how to implement those. And it's really these top 2. It's the S and the O that I find a lot more challenging. So the single responsibility principle, the open-close principle. So what are they? So the S and the O, so SRP, kind of an older definition. I couldn't find the exact time of this, but there should never be more than one reason for a class to change. In 2017, Robert Martin published his book, Clean Architecture, and kind of rephrased that as a module should be responsible to one and only one actor. Now again, Robert Martin is a general software author. He's not talking about CpplusPlus 20 modules here, but this is a generic, this is a group of functionality that goes together. The open-close principle. Software, entities, classes, modules, functions should be open for extension, but closed for modification. This was from Clean Code, Robert Martin, paraphrasing Bertrand Meyer. So whether you are hearing these for the first time today or you've been reading about these for decades, who felt like I'm going to take a poll, who felt like they understood these 2 when they first read them?
First one.
Yeah. I felt like, okay, I kind of get it. This OCP, what is closed to modification? That one was harder. So regardless of whether you felt like you really understood them, who later felt that your initial understanding was wrong, whatever that was? I guarantee my You could say wrong, you could say incomplete.
Incomplete.
So who still feels that the S and the O are hard to follow? Yeah, I struggle with these, right? I think that these are two difficult concepts. So let me hear your thoughts. What are some of the things that make S and O difficult to follow?
Complicated requirements.
Okay, so difficult inputs that you're trying to fulfill.
You mentioned it already a little bit, but part of the problem of these definitions for these sort of abstract ideas is there's not a clear mapping between them and whatever technology you're using. A lot of these books, they tend to be written from the perspective of I'm writing Java or I'm writing C#, and these concepts are much more clearly mapped into those languages and much harder to map into the tools that you have. You can sort of try to guess at what they might look like, but everyone's got a different idea about what that mapping is, and so you get a mess when you're actually trying to talk to other engineers about how to agree on these things.
Absolutely. I mean, varying points of view on how to do these.
Pointing behind
Yes. Nope.
you, pointing at me.
Yeah.
These two are actually in my point of view, these two are actually in tension. Because it's if you're following the open-close principle and you're extending something, it's actually quite easy to add to a function something, to add it to do something in addition to what it used to do. And then suddenly it's easy to lose the single responsibility thing. It's doing this and this.
Yeah, absolutely. Tony.
The one in single responsibility, or the single part of single responsibility, it's like our brains are so good at, oh, this is one thing. Like my example is always, it's just the camera. It's the camera class. It does everything camera. It's like, well, that's not one thing. That's a lot of things. But I can put one word on it and claim it's one thing, right? And it's like, oh, this whole, it just controls the robot. That's one thing, right? It's like single responsibility. It controls the whole robot. Maybe that's not single, right? But
Yeah. Well, that's a great setup. I'll get you the 20 later. So my reason, when I look at these just based on the definitions, the things that really trip me up is one reason with the SRP. What is one reason? When have we boiled that down enough? And then what is closed modification? I can certainly understand I've got my code open to extension. Yeah, I'll change my code all day, right? But closed modification. Some authors have actually postulated that OCP and that OCP is really an extension of SRP, that you can't really follow OCP. It's really that you have to do that. In his book, C++ Software Design, Klaus Egelberger contends that his point is we really need to consider how we extend our code. And the emphasis needs to be on how am I going to extend this? And that's really what you get out of OCP that's really different than single responsibility. So there are certain kind of problems that really bother me. And it's taken me from my childhood into adulthood to try and actually figure out what it is about these. And one of these is raking leaves. Raking leaves irked me. To some degree, it still does. And it took me a while to figure out why. Now, when you rake leaves, you could choose to rake no leaves, but that has problems. You can upset your neighbors. You could upset your homeowners association. You may hurt your grass, introduce more mold, whatever it is. So raking no leaves is not good. But on the other end of the spectrum, you can't rake all the leaves, can you? Right? Could you get every leaf in your yard? It's a fool's errand. You would be raking leaves to the end of time. You could put a box around it, but then your yard's not very useful and probably get other people mad and other reasons, right? But so what do? If we've got these two extremes, what do we do instead? We pick some arbitrary point in the middle where it's good enough, right? So my point is different than your point, it's different than your point, it's different than your point. What you would say is good enough for the yard. And I can tell you that my point for what's good enough today is going to be different than what's good enough tomorrow. And a lot of times, my point where it's good enough is when my wife comes outside and says, hey, Michael, it's probably good. Stop overdoing it. Come inside, right? I think that software ends up being a lot like raking leaves sometimes, software design in particular. So in the absence of clear, practical guidance, we have to pick some arbitrary point where we feel that we followed something, and that's hard. That arbitrary point can vary from person to person. So how do you decide when you've reduced something down to a single responsibility? What does that mean? How do you decide when you've done enough unit testing? I know we have things like code coverage metrics that give us a quantitative number, but if your requirement is 70%, is that really enough? Should you be doing 80? Was 50 enough? Did you need any? What is enough? And then, how do you help new or inexperienced teammates adhere to these standards? How do you do this when you bring someone on? Or how do you do this when you go to a new company? And now you've got your idea and they have theirs. So that's what we're going to talk about. We're going to talk about our method to try and answer this question and make this a little less artistry and maybe give a little more clear definitions on some things. So decision-making isolation, this is what I've coined, this methodology, this philosophy that we've talked about. DMI coming to rhymes with, kind of sounds like too much information, TMI, no, I don't know. It's also not an overloaded term. There's very few things with that acronym, so I thought that was kind of cool. All right, so this was the vision. Vision was the most important part of our code are the places where we decide what should happen. If those decisions are implemented correctly, then we can feel confident that our code is trying to do what we expect it to do. Doesn't say it's going to, but at least where we've chosen to make decisions, then we feel like we're trying to do that. And if these decisions are isolated, the code is easy to read, modify, extend, and test. So that's the vision for DMI, for what we're trying to do. Everyone got it? Cool. All right. Thanks for the talk. Yeah. So if you need help, if you're trying to figure out how do you end up doing something, if you need help, who are you going to call? Core guidelines, right? So the core guidelines, that is one of my big points today, that what we're going to look at next really is derived a lot from those. I've really gotten into reading the core guidelines a lot more in the last 2 years. Don't recommend anyone sit down and try to read them all the way through, but please, I will encourage you to refer to these. So I've mentioned decision-making isolation. What is it? How do we do it? So decision-making isolation is separating our decision-making into pure free functions or small classes without external dependencies. Then we're defaulting to using free functions and publicly available data, such as structs or variables, instead of classes. Only use a class if the data has invariance or is part of a component boundary. And then unit test all of our decision-making code thoroughly. So I'm going to take a sip of water and give you guys a sec to breathe on this. We're going to see this slide a bunch more times today. So these each map to different guidelines in the core guidelines. So if you're looking back at this later, you can see what these different ones are and how those map there. But again, core guidelines, very useful. As with any text, you could certainly manipulate those to say different messages as well. So this is how I've pulled these together. So before we really dive deep into these things, let's look at an example and kind of go shallow on this. So here's an example. We're going to see this a couple of times today. So it's a request handler. It's a really simple class. We've got an outputter. Yes, it's a raw pointer, but it cleans up the code, right? So that is injected in. It's a dependency that we inject into this class. And we're just going to look at one function, process request. So it does something pretty simple. It takes in a state and it then uses the outputter to send something based on that state. So if we consider this from our definition of software quality and S&O, is it readable? Sure. I mean, I think most 10-line functions are fairly readable. Not all, but certainly I'd say so. But you can imagine as this starts to grow, I realize it's a much maligned switch statement, yes. But you can still imagine as this code starts to grow, it's going to be harder and harder to read this. What about modifiability and extensibility? Well, sure, we can add another enum here, and we can certainly do that. But again, this is going to grow to be harder and harder to modify and extend. And then for testability, now testing this process request function has very little to do with the outputter, right? The outputter is just send something. That's pretty trivial. So, but now any test for process request has to be concerned with outputter. So in DMI, we're just touching on this, we'll come back to it. We separate our code into 3 types. We have decision making, where we're choosing what our code should do. Our I/O, I know I said I'm an embedded guy, but this is not hardware I/O, GPIO, I²C. This is code that either gathers data for the decision making or does something with the output of those decisions. All right, so that's our definition of I/O for today. It's not a great name, it's the best name I've come up with so far. So if you got a suggestion, let me know. And then wiring. Wiring is what glues those together. So I've refactored this with decision-making isolation. So I've pulled a function out into a namespace with a name that clearly correlates with the other class. And I've pulled out my decision-making. Now, when I decide what data I'm going to send, that's in a pure free function. Pure free function meaning data goes in, data comes out. There's no internal state that it's modifying or reading from. The I/O, well, outputter matches with the definition of input and output, right? So the outputter is here. And then this process request function is our wiring. That's what connects together where we made a decision and where we did something with that. So if we consider this back for quality, the decide function, is that easy to read? Yeah, I think that's pretty easy to read. Yes, it's still a switch statement, sorry. But it's easy to read. You can see what's going on because you know what comes in and you know what you're intending to get out. It has a single responsibility. You could certainly write it so it doesn't, yes. But it's easier to make something single responsibility when you have something that takes data in and delivers a decision out. In terms of modifiability and extensibility, why is decide going to change? Mostly because the decision that we want to make has changed. Not because outputter changed. So, and then for testability, we'll come back to that.
I like that slide.
Thanks. That's good encouragement in the middle. So here's our before and after. So you can see on the right, we've got a little bit more code. When we get to testing, we'll show, I think I don't have evidence to this, a lot of evidence yet, but I think that it switches a little bit when we get to testing. So we've got something now where we've broken out this decision and it looks a little bit different. So this is our base example. We're going to come back to this for at least once more in this presentation. And now, how do we do this? So how do we divide our code into our decision making, our I/O, and our wiring? So this was our first point, right? In order to do DMI, we're separating our decision making into pure free functions or small classes without external dependencies. So picky eaters. Who has a picky eater in their life? All right. Now, I won't ask you to raise your hand, but how many of you were thinking of yourself when you were considering that? Okay, a couple people. So I have 2 little girls under 4 years old. And I have a wife who's pretty picky too. So that's a challenge. Sometimes it is a challenge to figure out what to eat. So let's imagine for a moment that I had someone who was coming to take care of my kids. That's what my parents are doing tomorrow. So if I needed to write them out a flowchart, a physical piece of paper flowchart to decide what to make for dinner and to make it, what would that look like? Well, I think it might look something like this. Ask the parents what the kids ate recently, because heaven forbid you can't eat something too soon again, right? Look for the groceries we have in the refrigerator, groceries we have in the pantry. All right, now let's figure out what are we going to do. Have we had rice bowls lately? Okay, full disclosure, my kids don't eat rice bowls yet either, but we're trying. Then, okay, if we haven't, then do we have beans? Do we have rice? Great, sweet, let's get out the rice maker. Then we'll start talking about how we make rice, because if you've got any kind of picky 3-year-old at home, you know that the rice has to be right too, right? What if not? All right, then have we eaten nuggets this week? And then if not, then do we have nuggets and ketchup? Because no 3-year-old's gonna eat nuggets without ketchup. So then we're gonna go through and talk about how we get those out. Now, what happens when this changes? What happens when we've gotten them to introduce a new food, or when a food is no longer in fashion? Now I'm gonna have to redo this flowchart. What about when I do this flowchart and then I need to go talk to my wife and say, hey, we in agreement, this is a good flowchart? It's all together. It's all wound up in one thing. So what if we refactored it? What if we change this so that we've isolated right in the middle where we decide what we're gonna eat? Now that can change. Making rice isn't gonna change all that much. Microwaving some chicken nuggets is not gonna change all that much. But now I've isolated the decision. And that's really the key point, right? If my parents lost my instructions for making rice, they could make rice. If they lost the flowchart on how to make decisions, it could be a more interesting evening for them. So that's what we're trying to do with our code. We're trying to isolate our decision making. So we've got some working definitions. Again, this is work in progress. So our working definition of decision making is it determines what the code should do. So some attributes of that. So we're focused a lot on conditionals, non-trivial computations, branching structures. So a lot of times our if, while, those loops, those conditions, those things indicate, a lot of times that's our decision making. We'll see some examples where that's not always true and we have some simple decisions, but these often return flags or enums or other type of thing that indicate what action should be taken next. And these can be algorithms as well. So we heard from Tony yesterday, separate calculating from doing. Had that remembered before. So algorithms, say algorithms or decisions? Well, I think I put those in that category because when you make a decision, you take some data in and then you return a decision out. An algorithm may not make a decision in and on its own. I'm thinking a mathematical algorithm, not necessarily like a standard library algorithm, right? But you may compute something, you take data in, you return data out. So in my mind, they're synonymous. We're gonna call those part of decisions. So let's look at an example. So say we have a function where we're determining what pizza we're gonna order. In my life, I've got to see who's gonna be there. And based on who's present, we're gonna determine what kind of pizza we order, right? Now the different types of pizza don't necessarily matter in here, but this is pretty easy. It's pretty easy to read, pretty easy to modify. If I added another person in here, I could certainly do that. It's only gonna change because determining my pizza order changes. And in terms of testing, I've only got 8 possible conditions as inputs. I'm not really concerned if I'm gonna order Hawaiian pizza from California Pizza Kitchen and pepperoni from Papa John's. That's not part of this. This is determining what pizza we're gonna order. So in this case, we're returning an enum. In another case, we're gonna return a bool. So should we go out to eat? This could be a factor of energy level and who's there and what day of the week it is. So we've got a little more complex data. We don't have just 3 bools. Now we've got an int and testing. Yes, this is now we probably are gonna have a hard time testing the billions of possibilities for the data that come in, but this still becomes pretty easy to test our boundary conditions. But you can see one of the things in here is our energy level. Well, how do we get our energy level? Well, say we have an algorithm that I completely and utterly made up. But here we're taking in some floats and then ints, and then we're gonna return back an integer. So that's an algorithm that we're gonna compute. So this is what our decision making would look like. So these are different ways. You notice these don't do anything. They don't make any action. They're just trying to decide what our code should do. So something that, if you've seen talks like from Jason Turner and others, const expr is a hot term. I'm learning more about it right now. So when you separate things into these free functions, small classes, it is easier to make things const expr. I haven't explored this enough yet to know that I don't know that you're going to have a lot that is done at compile time, but you certainly have communicated to your compiler that this can be optimized as well. So you can imagine that big branching structure could be condensed down to something else. Now let's step into I/O. So this was our second category. So again, remember, this is gathering data for decision making or making some action based on the decisions. So this is our working definition that I just gave away. So gathers or supplies data for decision making or does something with those outputs. So we really categorize that this comes down to three different types. So we're either interacting with external code, like UI, hardware databases, messaging protocols. This could be your Qt. This could be your I2C bus, whatever it is. You've got something else where you have some other I/O, and we want to separate that. We're going to isolate that. So that could be something that gathers input or does our output. It could be a user-defined entity from just a different component. Maybe it's all logic, but it doesn't have anything to do with that. So that is our input and output from somewhere else. Or it could be direct calls in the wiring, where you're directly making calls into things. And we're going to look at all three of these right now. So this is another toy example. We've got some health monitor. We've got some function in to perform our health check. So if we drop down to the bottom, we've got two different things that we've injected into this class, presumably. We've got a health tracker and a warning notifier. So the health tracker is going to gather us some data about these subsystems' health. And then our warning notifier is going to do some output based on the health check. So we can see up that where those happen, that we gather things up at the top, and then in the bottom of the function, we notify if the condition is right. We've got our action function, get action. Yeah, it's very well described here, get action. And then we've got our third type, the third one on the previous slide, where this is a direct call to getting a clock. Now you might say, well, is that really I/O? That's not some external thing, that's part of the STL. But you can imagine when you think about testing this, now your unit testing has to worry about time. And I've done that, and it's not necessarily fun. And now you're guessing that when you run your system, that 1 millisecond on your system means 1 millisecond on your hardware. So I would consider that I/O in this particular case. So that's our I/O. These things are gathering things or doing output. Now what stitches these together is our wiring. So our working definition, it stitches together the decision-making in the I/O at a higher level of abstraction, so it is easy to read and understand. So some attributes of wiring. So it's describing how the data is gathered, how those decisions are made, and how the action is taken. So it's this description, right? That's the part that our wiring is. It tends to be boring, easy to read, and code review. And that's what we want. We want this code to be relatively boring. It's not making the decision as to what's supposed to happen. It's just supposed to connect it together. And often, due to these I/O dependencies, it's hard to unit test. So we don't. We're not going to unit test our wiring. We are going to test it. We'll come back to that. But we are not going to unit test that wiring. We're going to rely more on our code review and the fact that it should be simpler in order to make us feel confident at the level that we're writing that object. If that makes you uncomfortable, give pause a little bit. We'll come back to it. So I read clean code back in 2017, and this quote always stood out to me from Grady Booch. Clean code is simple and direct. Clean code reads like well-written prose. I always thought that was beautiful. Probably because prose is supposed to be beautiful, and that has some context to it, right? But clean code never obscures the designer's intent. And that's really what our wiring is supposed to do. Our wiring is supposed to be the part that you can read and follow what things are supposed to happen. So this is a really boiled down generic example of what our wiring could look like. It gathers some input, it makes there's some decision that's made, and then based on that decision, we do some output. And you can see here, I said a lot of our if statements and while loops and things like that indicate decision making. In this case, we've got pretty simple if statement that's in this code. You can imagine though, as that if state, that could grow, and then we might have to decide, do we have another place where we're making a decision here? So we've talked about how we separate things into these small classes or free functions. So how do we choose that? Well, it comes down largely to the concept of invariance. So again, we said that we're defaulting to using free functions or publicly available data, such as structs or variables, instead of classes. And we're only going to use a class if data has an invariance. We'll come to the second part in a minute. So what does that mean? Well, first, aren't classes and structs basically the same, right? Well, yes. Almost, right? They're fairly interchangeable. However, when you look at the core guidelines, they both say there's a convention. So a convention is that a struct has only public data members. It shouldn't have any private data members because our data members are public, so anyone can modify it. So what is your public data member, or what is your private function doing if anyone can come along and mess with your data? But these are conventions. I could imagine, I don't know, based on this, my theory is that if we went back to the early 1980s, that Bjarne might have chosen to make them more different. Maybe not. That's my theory. He's not here, so we can't ask him. So that's our convention. So if we look in the core guidelines, they give a definition of invariant. And we're not going to read this whole thing, but the first sentence, an invariant is a logical condition for the members of an object that a constructor must establish for the public member functions to assume. And that threw me off for about a year. Really? The constructor has to establish this? It just tripped me up every time I read this. Because what does the constructor have to do? Does the constructor have to do something to make that happen? So I've dug into this. I see some raised eyebrows. Give me just a moment. All right. So here is I'm going to redefine invariance a little bit, or maybe not redefine, but put this in my words where this is easier for me to understand. This is how I understand invariance. Because I don't think I'm saying something different. I'm going to give a little bit different explanation. So it's a logical condition for the members of an object that can be expected to be true from the time the constructor exits to the time that the destructor is called. And these fall in three categories. So again, from the time the constructor ends to the time the destructor is called. And what tripped me up is saying that a constructor has to establish it. What if my constructor doesn't do anything? What if it's part of my class, somewhere else in my class, where I enforce this invariant? And that's what I'm kind of stepping away from a little bit. So we've got three logical conditions, three different types of invariance. So it's a relationship between at least two data members such that all the members cannot vary independently. The second one is a guarantee that any function with access to a resource can be called at any time, which is RAII. The third one is similar to the first, a property of a data member that must always be true. So let's dive into these three. So this first one, at least two data members cannot vary independently. So what is this?
Physics homework.
Physics homework.
Yes.
Voltage resistance.
And
Ohm's law.
Ohm's law, yeah. And
Ohm's law.
I is
Current. So voltage is equal to current times resistance. So this comes from our basic physics classes, right? So this is always true for a simple circuit. All right, as far as I want to go in physics or electrical engineering, this is always true. So if our voltage increases, either our resistance has to increase or our current has to increase, or one of those has to go down, right? If our resistance was to go down, and for our voltage to remain constant, our current has to increase. So these cannot vary independently. They're always going to have that relationship. So if we were to write that in code, We couldn't have that as a struct. We can't just set voltage arbitrarily. We would have to do something where we are enforcing that if you set resistance with fixed voltage, then you're going to have to change your current. If you're going to change your resistance with fixed current, you're going to have to change your voltage, right? These are going to have to be true. So these have an invariance. They cannot vary independently. But not all variables have to impact all others. So if we've got this example where we have a light class and we set brightness, well, it might be that for this light, in order to set the brightness, it has to be on. So we're gonna have to look at our data member, is the light on, in order to determine if we're allowed to set the brightness. But maybe the flipped light status, you don't care what the brightness is in order to turn the light on or off. So in Ohm's law, all three of those things have to be in harmony. They can't change independently. But in our data, there is a relationship. It doesn't have to be in every direction. So that's our first type of invariance. So the second one is RAII. So resource allocation is initialization. We're not going to have to read this whole definition, but it literally says in the definition on CPP reference that this is a class invariant. So let's look at a simple example of that. So RAII, we're not going to dive deep into that. But what it says is that if we've got say we have a file handler, we're going to open that file in a class, and we're going to manage that resource. And then when the destructor is called, we're going to close that file. And if we get an exception during open, then we're guaranteed that we're going to call that destructor, right? Then any other public function in this class can be called at any time. Remember, invariance is a logical assertion. So you are guaranteed from the time the constructor exits, you can call read line at any time and not have to worry if that file has been closed. That's what RAII says. Now, for my piece, I prefer the acronym cadre. For constructor requires, destructor releases. I find this to be a lot easier to remember what it means. But really, of course, our challenge is that it's hard to change any definition that's been around longer than the Super Nintendo. So this is helpful for me to try and remember what RAII means. Maybe that's helpful to you. Bjarne has also come out and has said many, many times that he doesn't like the term either. But sometimes things stick, right? So let's look at this last type of invariance. It's a property of a data member that must always be true. So this is similar to that first one, right? It's similar where we have some relationship, but it's usually a comparison to a constant or a literal. However, and we often see these in our non-trivial getters and setters. These could be algorithms that enforce that invariant. So let's look at these. So we have an even number class. So we create the class and we set the number in the constructor, and then we go through and make sure that whatever we've passed in is an even number. Now you can imagine any other thing that calls from this even number class can be guaranteed that they're getting an even number. But there's nothing where you're comparing between two data members. There's no invariance there to another one. Right now, this class doesn't even have another data member to compare to. It's compared to 2. That is our invariance. You could say it's also the 0 is also part of the invariance there. That is the invariant here. We could also have an algorithm. So if we had a unit circle class, we said the only circles out there are unit circles, right? Everything else is a scaling factor in that. So if we have a unit circle class, we might want to bound that angle. So when you set the angle from degrees, as we convert that to radians, we're always going to bound that between 0 and 360. So that would be an example of where we've got an algorithm that is enforcing the invariant, that this is always going to give you an angle between 0 and 360. So let's review. So we said we're going to use a class only when our data has an invariant. So it's a relationship between two data members such that they all can't vary independently. We have RAII, where we're managing a resource, And then we have a property of a data member that must always be true. So let's try this out. Let's go through, we've seen a couple of examples. Let's go through something more tangible, right? So say we've got a date. We're going to create some entity for date. Can this be just a struct, or do we need a class? We need a class. We can't just arbitrarily set our day to day 60. We can't set our year to year 0. So we have relationship between these two. There's no September 23rd or September 32nd. There is a 23rd. So we're going to declare a class here. So we've got a class where you pass in the day, month, and year, and you have some other function where you could set the day. We're going to store these as 3 ints. Could definitely do them differently. But this is what it might look like. So we are going to go ahead and we're going to have some helper functions. So we're good. We're doing decision-making isolation here. We've pulled out our things that are making the decision. And then our setDay class is also going to enforce this invariant. So this is what our helpers might look like, where we have some that are going to enforce, is the year valid? So that's pretty standalone. A valid year is independent of any other things in there. Is it a valid month? That's pretty standard. That's pretty simple as well. But we know that day is coupled to both of those. You have to know, is it a leap year? How many days are in the month? So we have this relationship. We have to enforce that invariant, but we've separated them out. Now, can you imagine if you needed to write tests for these functions? They're pretty straightforward.
Yeah.
I feel confident that I could write the tests for these. And if I feel that these are confident, that these are right, I can feel pretty good that that day class is going to be right too. But what if some of our data doesn't have an invariant, right? We have, yes, some of this data does, but some of it doesn't. How do we do that? So here's my proposition. So say we have these different data members. We have an ID and we have a healthy status that don't have anything to do with when we receive some message. So we have this data received, and whenever we get our data, we also want to store the time we got that data. Maybe we have to receive the data at a certain time after the system boots, or however frequently, whatever it is. We've got some point where we need to know that if we've ever received that. So those two have to be set together. We're not going to set those as part of a struct. So if we have our data received, so what we're going to do is we're going to pull those two data members out into a data received class. So we're going to have is data received, and then we're going to have time. So we're going to store both of those. Now, one thing that I did just want to point out, you notice the constructor here takes a function that gives us time rather than making a direct call to steady clock or something like that. Because now this class doesn't depend on me getting a clock. I can set the time however I want to. Makes this easier to test. So now we've encapsulated this invariance. Those two are going to be set true when the set data received class or function is called. And then I'm going to put those into a struct. So these other two pieces of data, ID number and is status healthy, those can vary independently. So I'm going to take my invariance, encapsulate it in a class, then put that into a struct. Now, another option is that you could use a standard optional. And now I've implied to my reader that my user, whoever it is, that if time data received is a null opt, that it's not been received. You could argue that that's maybe a way to use the language to avoid using class, that you've kind of implied those. I don't know. When I implemented this in my code recently, I decided I wanted to keep them explicit, that someone didn't have to kind of intuit that that being a null opt meant that it hadn't been received. But anytime I think that you can use constructs from the language in order to avoid, maybe not anytime, but if you can use constructs from the language to enforce things, then that's a good thing. So remember, an invariant is a logical assertion, something that must remain true. It doesn't mean immutable, right? I've had confusion with people that are kind of newer to these terms. So an invariant is a logical assertion. Now, you might be wondering by this point in the talk, why so much emphasis on free functions? Someone at work actually called me Captain Free Function the other day. Well, unfortunately, I'm not going to tell you to some degree. I really like free functions. I've given you some of the reasons why. But if you really want to learn more about them, I can't state this better than these guys have. There's a phenomenal talk that really changed the way I wrote code from Klaus Egelberger in 2017, where he discusses how free functions improve encapsulation, abstraction, polymorphism, cohesion, flexibility, extensibility, reuse, generality, testability, and performance. It's great. I highly recommend that talk. Going back to 2000, Scott Myers wrote an article in Dr. Dobbs' journal, How Non-Member Functions Improve Encapsulation. And I think in that article, he really flips. He takes some of the big arguments against preferring free functions and flips them, and really was a really impactful one. That one's a little harder to find with Dr. Dobbs' journal being archived. Third one, this article from Herb Sutter, I can't figure out the date on it. This doesn't seem to be clear on his website, but he rewrote the C++98 standard string function that had 103 member functions. I have no idea how many it has now, but it had 103 and 98. More, right? He rewrote those as 32 member functions and 71 free functions. That was pretty cool to see. And then the one that I've found to be the most well-known, emphasizing free functions, Effective C++ third edition from Scott Myers, item 23, page 98. Prefer non-member, non-friend functions to member functions. So great resources here, definitely some good reading. And my slides are already up on the Discord channel if you want to refer back to this. All right, we're gonna take 30 seconds. You guys have been listening to me talk for quite a while. It's a long day. So you guys can go ahead and stand up. We're gonna take a 30-second break. I'm gonna stretch out, but I know you guys are probably ready to stand and stretch a little bit.
Only had known that a minute ago.
Sorry. All right, we're gonna go ahead and keep moving on, take this to the finish line. So there is an exception. There's an exception to this definition. I've said that invariance is the reason we'd use a class over a struct and why we might use a class over free functions. But there is an exception to this. There's an exception to any good rule, right? And that is component boundaries. So referring back to what is decision-making isolation. So this is where we're going to talk about, we would use a class if the data is part of a component boundary. So when we talk about entities, entities are our functions, our classes, our free functions, lambdas. Entities is kind of our generic term. Our entities are grouped into components, and those components tend to be grouped into our applications. Now, unfortunately, guidance on designing a component, really defining exactly how do you divide up your components, is out of scope. As I started building this talk, it went on a whole new rabbit hole, and that really could be a whole talk in and of itself. So, see clean architecture from Robert Martin. Domain-driven design is something that I've just started looking into, something I'm looking forward to getting into after this presentation. But those are great resources if you want to get more into how we're going to divide things into our components. So a little bit of a cop-out here. This is an area that I'm still exploring as part of decision-making isolation. So let me ask you guys a question. What are the reasons, besides an invariant, that you would choose to use a class?
Encapsulation.
Complexity.
Encapsulation? Can you explain more? What are you encapsulating?
If I have some sort of construct that I don't really care to be visible or externally visible, and I want that to be a little more fluid, if I need to change that for some reason, then I would encapsulate it.
Okay. So maybe that's kind of its own thing. It's its own maybe component, or maybe it's its own thing that we're trying to separate from some other piece. Okay.
That's what I was going to say. Is just like, I want to change this class later. I'm going to change these member variables. So I just don't want you to touch them. You know, like, it's like implementation detail. Maybe they don't have invariants, but like, I just unsure of the future of it. So it's like, let me just keep this behind.
Okay. So thinking about OCP, how we're going to extend this in the future, how we may modify that.
You're trying to hide complexity that is unnecessary for the end user of the class.
Probably
Okay.
because there's invariants, though.
Maybe. It could be that you have some kind of an API boundary. You've tried to hide some details or try to simplify something for your user. Yeah, absolutely.
Or if it's an API that behind might have multiple implementation, whether say it has an external resource, you might get it from a network, from a file, from a database, or whatever.
Sure. So polymorphism at that point could be. So here were a couple of reasons I came up with. Again, this is a work in progress. This is something that I'm hoping to learn more about. So maybe we've got an API that encapsulates a component. We're trying to, again, simplify things down. So we're trying to give someone some interface, not abstract base class interface, some interface where they're using some other piece of code. Maybe we're trying to fulfill the dependency inversion principle. So anyone that's read clean architecture, there are different layers, and if you want to access something from a different layer, then you usually will try and do dependency inversion principle to depend on that interface, that abstract base class, instead of depending on a concrete thing. And then we may have runtime polymorphism. There might be times where we need to do polymorphism, so we're going to choose to use a class. Now, there's obviously lots of options for compile time polymorphism, or that you can do as well, link time polymorphism. There's lots of ways to do polymorphism as well that may or may not do that. But where we need to divide things into components and how we go about doing that may supersede their definition of invariant. So we'll see how that develops. If you've got more ideas on this, please, I'd be more than happy to chat at the end of this presentation or afterwards or later this week. So in DMI, these classes tend to be our IO, right? We're going to try, if we're choosing to make something a class because it's in a different component, we want that to be our IO, something that is either gathering data or making some action most of the time. So let's take a step back towards the beginning. We talked about DMI, we've talked about single responsibility principle, we've talked about open-close principle. So how do these relate? So remember, these were our definitions. SRP, there should only be one reason for a class to change. Open-close principle, Software should be open to extension but closed to modification. So how do DMI and single responsibility principle play together? So our decision making, being in free functions or small classes, makes it easier for those to do one thing. Does not guarantee it. There are very few guarantees. There are no absolutes, right? Except for only the Sith make statements in absolutes. Classes that encapsulate an invariance should do one thing, right? We're trying to encapsulate our invariance, so that helps us fulfill single responsibility. And then when we consider our wiring, we really do need to consider if more than one actor could cause that to change. So there's a lot of scrutiny that I think we need to put into the wiring in particular, because that can definitely do more than one thing. So what about open-close principle? So our decision making is only going to change when the decision changes. It could change because of the input data that we're putting in, but really, you want to try and isolate your decisions so they're getting just the data. We're not going to pass the whole class in. We're going to pass in the data members that we care about, the things that come from that I/O in order to make that decision. Our invariance keeps those classes focused. And then the I/O can change without impacting our decision making. So those being external things, that allows us those could be modified without changing our decision making. So we're open to those modifying, being extended. And then our component boundaries. That's where we've provided a scene for polymorphism, where classic definition of OCP is where you have some kind of interface, some abstract based class where you could swap things in and out without impacting the code that uses it. So our component boundaries in DMI do provide for that. All right, so I promised we talked about unit testing. We're finally there. So this is what started it all, right? This is where I have a lot of passion around unit testing, and this is what started this whole idea of DMI. So we're going to unit test this decision-making thoroughly. So remember our revised focus. We're going to try and get better at choosing what code to test and designing code that is testable rather than getting better at writing more complex tests. The goal of testing is to build confidence that our software works. Right? And this is not unit testing, this is all testing. Let's think about back to the leaves. We're not trying to rake every leaf, we're trying to rake enough leaves. We're not doing formal methods. We're not trying to prove our software works. We're trying to build enough confidence that our software works. Even in medical device development, when I'm working on a device that's used in brain surgery, I can't prove that it works. I have to be confident that it's going to work. So, by isolating our decisions, it's easier to feel confident that it's doing that. So let's look back at our determining our pizza order function. So if we're testing this, sorry, the text is going to be a little small for those in the back. You can imagine we could write tests, I use gtest, where we're able to test every input and refer every output. This is simple, this is easy, this is clear intent, clear what the test is supposed to do, very clear if this test breaks and why. These tests break and why. And you can imagine open-close principle applies to our test code too, right? It's been said by people, our unit test code should be a first-class citizen. We should be treating our unit test code at similar standards to our production code. Otherwise, our unit test code goes downhill, right? So you can imagine these tests are easy to extend and modify. If we think back to the should we go out to eat function, we're not going to look at the test for this, but this is going to be similar. You can imagine how we would test this. We've got different parameters in. We're going to test our boundary conditions instead of testing everything like the last one, but this is easy to test. Same thing with our algorithm. Now we're really having to choose what we do is with floats coming in and out, but again, the decision making is easy to test. Now, this is our request handler function that we started with back at the beginning. And this is the before and the refactored afterwards. So let's look at how we would test this request handler, the original version. Now I have this outputter that I inject. So we're going to need an outputter if we want to test this, right? Now we could use a mock here. Personally, I'm not a big fan of mocking frameworks because you try and get them to do too much, and I've tended to not read enough about why. So I think at some point I'm going to do maybe a lightning talk on using too many expect calls and what it actually says you're allowed to do with that in gmock. But we're going to have to create something. So it could be a spy. So in this case, I've done a spy because I'm actually seeing what the data is. I'm assuming outputter doesn't has a non-trivial, or has a constructor where I don't have to do a lot, or it doesn't depend on something that I can't do in this unit test. And now I'm gonna write my test to do stuff, and then I'll look at the data, and then I'm gonna do what I've instrumented. But now I have to maintain this spy outputter. Now if outputter changes, this request handler test breaks. Why? That has nothing to do with the outputter. I want to know, is the decision right? Right? When I want to know that when I pass this data in, that my code is going to try and send something, the right thing. If I've gotten all the way through my code and now I need to check what outputter got, is that really what I'm trying to get to in this test? Well, I think in a lot of cases what you want to know is, did you actually make the right decision? We'll come back. Hold on, like a couple slides. We're getting there.
Yep.
Now, if we think about, we've separated these decisions out. Now I've got something that's pretty easy to test. All right, so if we compare these tests, remember I said earlier, the refactored code where I pulled things out into another namespace, that code got longer. In this case, we don't have a spy outputter that we have to maintain. So now our unit tests maybe get shorter. We'll see. I want to explore that as we go. So the goal of unit testing our decisions in DMI is to feel confident that our software is trying to do what we expect. It doesn't say we're going to, it says we're trying to. Now, what about testing the wiring, right? This is where I've been saying we're getting to. My theory, or what I am advocating for, is that we're going to write automated tests. We are not going to leave this code completely unautomated tested, but we're going to group these at some level where it makes sense. Fuzzy enough guidance? Yes, sorry. Again, work in progress, right? But we're going to group things at the highest level we can where things make sense. Maybe not the highest level, but at a higher level. We're not necessarily going to test every single class. And it might be that you use gtest. That's probably my plan the next time I do this. This is what I have done when I have done this, is I'm writing things that look like unit tests, but I'm going to focus on happy paths. So if we look back at this code here, if I have a couple of tests that run through a couple of cases here, I'm going to feel pretty confident that things are wired together. I don't need to test every single edge case. And then as I've grouped things together, maybe I can group together an outputter and a request handler, and I can do those together. Maybe I can group those. So now I'm actually using the concrete classes. I'm not doing those. I'm not using mocks or spies. Maybe I need to do spies or different test doubles at that point. But the big point here is that I'm going to try and focus on a few happy paths. Why? We said our goal is to get value out of our unit tests, right? How much value do I get out of testing a couple happy paths? As you keep going and testing more and more corner cases, you're getting diminishing returns. So that's my proposition, that by trying to group things together, testing some happy paths, thoroughly testing all our decision making, we can feel pretty confident that our code is doing what it needs to do. It doesn't replace going and putting code on the system. We're still going to need to deploy and test that there. So what about testing our frameworks and drivers? So I think that there's a lot of value. My vision is the next time I get a chip that I need to write to, I'm going to write unit tests that are going to toggle that chip. They're going to set the bits, send the message, whatever it is. But I'm going to do that focused on that specific thing. It's not focused on the decisions, not focused on some higher level logic, what I'm trying to do with it. I want to prove that I can send this message over a spy bus. and I'm going to write an automated test that's going to do that. A huge key here, though, is that this needs to be separately executable from my unit test. So the test that I want to run continuously in my red-green refactor cycle, if you're doing TDD, or the test that I want my developers to be running regularly, that's not going to have anything to do with this hardware stuff. I want to be able to go and run that in some other executable. It's usually going to be a different binary, but it's going to be executable separately. In some cases, you may have tests for your wiring that might do the same thing, but I would consider those integration tests. I know terminology, testing, it's hard. Someone else probably has a different definition of integration test, but I'm integrating different components or different classes together, different entities together. But I want to write these tests but the problem that I find a lot of times when you get into testing your IO is that now you're making a lot of guesses about what your IO is going to do. You're making assumptions in your spies, your mocks, those kinds of things. So I mentioned test-driven development. It's something I'm excited about, really interested in. I don't have a tremendous amount of experience. I've done this some myself, still getting better at it. Certainly not something I feel that I have expertise in, but we'll see how that impacts and evolves things. All right, let's take it to the end here. So let's talk about our key takeaways. So we've seen this slide a number of times. What is decision-making isolation? We're separating our decisions into pure free functions or small classes without external dependencies. We're defaulting to using free functions, publicly available data, instead of classes, unless we have an invariant or a component boundary, and we're going to unit test our decision-making thoroughly. Now, this is an iterative process. In our example for date, yes, you could probably think through that, but as code grows and evolves, what's decision-making, what's wiring, what's IO, these things are this is iterative. You don't come up with the answer right away. You may have times where you go ahead and draw a component boundary where you've separated things that you expect to change, but it should be iterative. Did that actually need to be, or should that be something you refactor? Now, what makes this unique? I've presented a lot of ideas here that I don't think are necessarily unique. What's a little bit different, actually, and if you look at Test-Driven Development by Example, book from 2000 or 2002 by Kent Beck, he advocates for a lot of this as the extract method. And in Separation of Concerns, within that in C++ Software Design by Klaus, he talks about this too. Tony mentioned a lot of this in his talk yesterday, right? So what am I proposing that's slightly different here? It's the emphasis. So it's the emphasis that we're going to default to writing free functions. We're going to start doing structured code, and then we're going to choose to do classes where it makes sense, where we need to do that. Notice I didn't talk about architecture. I'm not talking, so that's kind of unexplored, kind of top-down, big-level architecture here. But that's what we're trying to do, is isolate our decisions in DMI. So what would I have you do coming out of this talk? So here's my call to action. First, use the CPP core guidelines. They really have a lot of guidance on a lot of areas. They're really well thought out. They're consistent. They have typos in them that are kind of fun sometimes. Then focus your unit testing on value. Whatever effort you're putting into your unit tests, that cost should outweigh the confidence you're building that your code works. Then consider invariance when you're designing your classes. Maybe I've given a little bit different definition here, or maybe I've given more examples of what invariance means, not a new definition, but maybe I've helped clarify that at least the way I understand invariance now. Use more free functions. Go check out that video from Klaus or the other articles there to see more about that. And maybe just maybe, try decision-making isolation. So again, I'll put this stuff up I'm hoping that I'll have some articles up on the blog in the next couple of weeks here, and maybe that's a place you could refer to. Now, I'd be remiss here, particularly at my first talk, if I didn't give some thanks. So first, I want to thank my wife, Jess, who has done a lot. Any of the graphics in this presentation that you thought looked good probably were done by her. So big thanks to her, a lot of nights away working on this. Matt St. Clair, I mentioned him earlier. He's been a huge co-collaborator on this. Really, this all started as his brainchild that I've just kind of taken and run with. Joe Barnier is another colleague of mine who's been a big collaborator. Big thanks to Plexus for sending me here today, for sponsoring this, and for supporting me in this endeavor, and my colleagues for helping me get ready, and to Klaus Egelberger, who I met last fall, and I probably wouldn't be presenting today without his encouragement. So with that, I want to thank you all again for being here today. Happy to chat about this now or the rest of this week, and hope you guys have a great rest of your time here at CppNow. Yes.
You had a question 4 or 5 slides ago about testing your decision-making process, and then maybe not so much testing the things that call it. And from my point of view, I think that you need to test both of them. You need to test that your decision-making process is correct, but also that the things that call it use it correctly. And if you test them both and one of them fails and the other one doesn't, or they both fail, you have a pretty darn good idea on what you're doing wrong, what has gone wrong, I should say. So I'm a big fan of having lots and lots of tests.
So I would question then, my proposition was that you do test the wiring, but we're going to do it maybe at a higher level. We're going to try and test fewer cases, because I think that a few cases give you a lot of value. The more cases you do, give less value, is my theory.
That kind of depends on the situation you were in.
It depends. All right. I can live with that.
If you have a lot of users that are using your code, the more tests you have, the more value you get out of it, because you find problems before your customers do, and it's a lot easier to fix stuff that they don't know about, that they just stay happy. And you're like, oh boy, I broke that. Oh, that's terrible. I found an awful bug. Has any of my customers found it? No, not yet. Great. I can fix this.
No, I don't disagree. I think that my focus is on where are we getting the most value, because I think that a lot of times I've been on projects where unit testing was just abandoned because it became such a burden. There was so much coupling. Every time you changed anything, things broke, which speaks to software design, architecture,
yes,
sure.
Does.
But that's where I'm saying I'm starting with focus on tests for the most value and then go from there. But I don't disagree.
Yeah.
Somebody else had a question up first. Yes.
Suppose you've separated out the decision making for some class into a separate free function. Do you think that free function should be part of the same module that the class is part of? Do you think it should be off in its own module?
So I think it should be part of the same. I think it's core guideline C.5 that says that your functions, your free functions, your helper functions, and that class are all part of that class's interface. So I think that those should be in the same module. Where it comes maybe into question is, one of those benefits of free functions is now I can reuse this, right? So I can reuse that. So then if you're starting to reuse it, then it calls into question, what does that actually, what is that? Is that its own thing that you should be separating out? We heard from Tony yesterday. Now, if you go ahead and couple things, now if these two classes are both using these free functions, they're really maybe part of an implicit data structure potentially. So, you always have trade-offs that you have to make where you put those. But as a starting point, I would consider those free functions to be part of the same module. So those would go together. Thank you.
Yeah. Yes, I really liked your breakdown into the 3 parts of like I/O, decision making, and wiring. But I think on the slide where you first showed that, you described wiring as like boring, easy code. And I guess I find in my experience that a lot of wiring can very easily have a lot of complexity in it, and I do find bugs in it, and they could just be like poor design to get the wiring to that state. So I guess I don't have so much of a question, but I guess I just want to echo some of Marshall's concerns that I feel like I do frequently find bugs in the wiring, and if I don't have test coverage of the wiring, and the happy path coverage you suggest certainly could catch some of them.
But then your wiring probably has decisions in it.
Yeah.
Yeah. So I think that that's a question there is, where, and I could not look at any code that someone's written and definitively tell you, well, this is definitely decision making. This is definitely wiring.
Yeah.
But it might be a question of that definition of single responsibility principle, one actor should cause this module to change. Who is the actor that causes that decision to change? So if you look at code and you say, well, there's one person that's going to cause this part of my code to change, maybe that's a place to separate that out into a free function, a separate class. Yes.
I noticed a lot when we were taking a look at examples of the decision-making code is that they separating out into free functions tended to, the examples tended to be pure functions as well, or at least they didn't involve state changing as part of the input to different things. And I don't know necessarily if you meant to exclude state changing functions or like things that will, alter the state of their arguments or some other state in the world. But when, especially because the way I would think about that is anything that, any function that needs to mutate external or even past in state ends up looking more like a wiring function from your perspective. So I think one of the really powerful things about the way you described those free functions was that they tended to be more pure in the way that they were computing their data, which is a very easy thing which is why I think they come up to be very testable. When it comes to things like wiring functions, which may in fact be interacting with IO type things, one of the things that I tend to worry about when kind of writing code that's interfacing with similar types of problems is the IO stuff can sometimes arbitrarily fail in like surprising and bizarre ways. And I'm wondering, like, as part of the testing of your wiring, right? I know you're arguing to take wiring tests out of unit and mocks and put it in sort of a higher level, like integration point. Like what consideration for arbitrary failures, whether they be like network, disk, or things like that, how would you think about testing those types of failures?
Yeah, so a couple of points in there. So yes, I would advocate that your decision making as much as possible should, I almost made an absolute. I would contend that my default is always going to be a pure function if I can, because I don't want to test state in there. If you're changing state, there's somewhat of an implied invariant in there, right? Some data is causing that state to change. So I don't want to have that in there. Maybe. I haven't thought through that statement fully. But as much as we can lean towards our decision making being pure free functions or classes where the invariant is enforced, that's what we're going to do. So if we have some class that has a state, we're going to pass that state in. We're not going to pass the class in and modify that in our free functions. So there, as far as testing other things, remember IO gathers data or does something with it. It doesn't necessarily mean our messaging protocol, our database access. I would contend that when you're testing those, that should be its own thing. And we're going to focus on, if I've got a database queries, I'm going to have tests that are going to test, do this database query, do this thing. And I'm not going to try and mock that. I want to write tests that are going to go do it, right? I want to go and as much as I can have a separate binary that I can run on occasion, maybe in CI if you're lucky enough, but where you can go and do that in a case, because otherwise, yes, you certainly value out of interpreting what you get from your database, but I'm going to try and do that as much as I can in real tests.
Right. But digging into that a bit more, if I write a test that says like go out to a database and go do this, right? In that environment, are you also simulating cases where like you don't have a database? Database is down, right? Like network's down. Like I would imagine that in the wiring code, there is logic to be like, oh, my IO thing errored in some sort of strange way and has some decision-making function that it needs to then call to figure out how to deal with that error.
Sure.
You could probably test the decision-making code, but I would also, I think similar to what has already been said, but it's an example of like the wiring needs to then, I need to be more confident that the wiring is handling an error when it occurs. Whether or not it does the right thing is maybe a separate question. Maybe that's what the free function tests. but like, how do I, in that integration test environment, create the errors that would allow me to actually test that part of the wiring code?
Yeah, you may, and I'm giving a soft answer that yes, there are definitely
that's fine.
cases where you're going to need to, where the best answer is a test double. Right? The best answer to test the wiring, you've got some critical entity that I need to make sure this thing works. Yeah, I am not opposed to saying we need to add more testing here because this is critical or this is buggy or this is error prone, whatever it is. That I think that's fine. You just have to always weigh, now we have something else we need to maintain. So am I getting the value out of this? But I'm leaning more towards trying to, maybe you don't need to build your whole app, but can I build a smaller integration test app that can go and combine a couple of things together and then go do that error handling? Can I create that error situation? Maybe you can, maybe you can't. I mean, we've got a number of bugs that we can't. So maybe there I've got to use a test double. But we're trying to build confidence.
It's time.
It's time.
Well, it's officially lunch, but everyone's free to stay.
Okay. I'll hang out. Again, thank you guys so much. I really appreciate it. And I'll see you this week.